Le professeur Ken Sakamura, qui nous vient du Japon et nous fait l'honneur de sa présence, vient témoigner des mérites de l'architecture ouverte grâce à l'Internet des objets. Et il nous parle du projet TRON, dont il est le leader depuis 1984. On peut l'applaudir.
My talk is titled UID Architecture, Open Architecture for the IoT and TRON project. Today I'm going to talk about the advantage of our open architecture based on our experience in Japan. In so doing, I will introduce UID architecture, which has been designed and proposed by my laboratory. I will also talk about TRON project, which has been in the background of these activities. Lastly, I will touch some future applications of the IoT that can be built using these technologies based on open architecture. I hope you will find out that open architecture approach is very useful in real world. You can obtain my slide from the URL shown in the screen, http://www.t-engine.org. I will use the case study of maintenance of the fire alarms and smoke detectors in Japan to show the real-world advantage of open approach. This is a photo of a smoke detector and alarm. Our handheld terminal scans the tag on it to run the product information. The tag and terminal are used daily in Japan. Today, our installation of fire alarms or smoke detectors in buildings and people's homes are legally mandated in Japan. When the law was enacted several years ago, the talk of traceability of these devices came up among building owners, landlords, construction companies, and building maintenance companies. What is a traceability? It can mean different things to different parties. But basically, it means that we can learn information such as when, where, and who produced smoke detectors, or when, where, and who installed the detectors. Such information is useful for maintenance and recall service of detectors. When this topic of traceability came up, an organization called Center for Better Living came to us and decided to use the following approach. Let us assign a unique identification number to detectors and make it possible to retrieve traceability information from database by the internet. The adopted identifier is called UCode, and it is stored in a tag that is pasted to the alarms detectors. This is an alarm with a CBA label, Center for Better Living label. The label has an RFID tag chip inside, and that stores UCode, the identification number. The chip on the left is used in the RFID tag. This RFID chip communicates at 2.45 gigahertz and costs about 10 US cents. It is relatively inexpensive for an RFID chip, but it can store only 128 bits. There is no way we can store all the product and the installation information in the tag. What is why we came up with the UID architecture concept, where we store all the information in servers in the cloud and store only identification numbers that is, U-codes in the tags. They are tags that can store more data, but they are expensive. If you would like to lower the cost of tag, you can use printed QR code, for example, two-dimensional barcode system. U-code is a logical identifier and is independent of the tag which stores it. Today, 900 MHz RFID chip on the right is more widely used than 2.45 GHz chip. This diagram shows the basic principle of UID, our architecture and application framework. We assign unique identification number to object or prices as well. The identification number U-code is stored in a tag and attached to an object or installed in a random place. A user reads the number with a terminal, and then through our process called resolution, obtains relevant information related to the object or prices. Quite straightforward, isn't it? Let me show you a short video clip to review this idea.
Ubiquitous computing. With ubiquitous ID or UID architecture, we assign a simple 128-bit ID number, a number called a U-code, to objects and places we want to identify. By itself, the U-code is meaningless. But when we send the U-code to a server on a computer network, we can retrieve information associated with it from information servers. A process called resolution takes place, and we obtain an address. Often, this is an internet URL one can access to obtain useful information. Since we use network access to obtain the meaning for each U-code, access is controlled at the network access stage. We can grant access to different information at different times, based on who, when, or where they are. The number of IDs in the ID space is 2 to the power of 128, a huge number. Even if 1 trillion people assigned unique U-code values to 1 trillion objects every day for 1 trillion years, we would still not have used up all the U-code space. There are no a priori meanings assigned to the U-code bit fields, so it is relatively easy to embed shorter legacy product code systems in U-code space because no collisions of meanings assigned to bit fields are likely. Everything we want to identify, namely objects and places, are tagged. This is why we use so many different types of tags to meet application needs such as cost, physical characteristics, etc. Our approach is tag agnostic. We can use any type of tag.
Our important features of U-code and UID architecture are as follows. It is open in the sense that U-code is not tied to a single company. It can be used across companies. A single building needs to manage many different types of detectors and alarms from many manufacturers. It is simpler to use our unified identification system for all of them. The manufacturing and installation information is available from the cloud with suitable access control to every party, the landlord, maintenance company, etc. This is a diagram of the system implemented by Center for Better Living. Collection of database, of product, and installation information is managed by CBL. Thanks to open nature of UID architecture, our manufacturers of firearms obtain the CBL label with tags inside their products and place the product traceability information into the CBL's database. Again, due to open nature of UID architecture, this information is shared by many parties, including manufacturers, construction companies, installation service companies, and landlord. Now the system is used by almost 40 companies and 2.5 million U-code are used as of October 2012. UID architecture concept itself has been proposed and refined by YRP, a ubiquitous networking laboratory. However, the promotion and maintenance is done by our third party, namely UID Center, a non-profit organization. YRP Ubiquitous Networking Laboratory, YRP UNL for short, is a laboratory of R&D on ubiquitous computing, or the IoT in other words, located in Tokyo, Japan. It has proposed UID architecture and now is a major member of UID Center. I am the director of YRP UNL. YRP UNL has worked with EU partners through various activities such as FP7 Casaglass. UID Center that manages U-Code is part of another NPO, non-profit organization called T-Engine Forum. The logos in the upper right corner of these slides are the ones used by these two NPOs. A computer project called TRON project, established in 1984, has been behind these activities all along. I have led the project since its inception. For example, the basic concept of UID architecture can be traced back to TRON project also. The TRON project has envisioned so-called intelligent objects since 1980s. Intelligent objects are networked nodes with sensors and actuators. They act in a cooperative manner to offer better service to human users. Our TRON project aims at producing the basic technologies for making such vision possible. In TRON project, we employ both the bottom-up approach to build basic technologies such as real-time operating system, embedded real-time operating system, and the top-down approach to predict and study future applications to run the requirements for basic technologies. TRON, our project has adopted the philosophy of open architecture. It has produced a family of real-time operating systems for embedded computer systems. Source code and specifications have been made available to the public for free. These activities of TRON project have been presented in Open Source for Embedded Systems track earlier this afternoon. A standard is important to assure openness and access. So we have worked with international standard developing organizations to produce standards based on U-Code and UID architecture to assure openness and access. For the IoT, the society-wide technological infrastructure will become necessary. Open and universal infrastructure that can be used by anybody will be important. Interoperability, extensibility, or scalability will be important also. IOTA, a European Internet of Things Alliance, shares this vision and has been working with us. IOTA has 6 founding members shown in the slide. One is it aims is to work with YRP UNL to collaborate on the R&D of embedded systems and ubiquitous identification technology. Participation inquiries will be welcome. This is a banner of IOTA shown at the IoT Week event in Venice or in Italy in June this year. IOTA had its first meeting there. This photo is from the MOU, a Memory of Understanding signing ceremony that take place in December last year, 2011, in Tokyo, Japan. This paid by the way to establishing IOTA this year. The gentleman are Mr. Koryonen Tattoo from VTT and Mr. Alexander Bassi of Bassi Consulting. A cadet of University of Roma, Sabiento had signed a MOU with YRP UNL, a scholarly R&D work. Professor Carlo Medacubio, assistant manager of CADID, is on the right. CADID is interested in the use of UID technology and two-kernel real-time operating system in their R&D work. I will now describe the IoT applications of UCODE today and in the future. In ubiquitous computing, or IoT as it is often called, the communication between objects and human is very important. Communication between human and object is the information flow with when I discuss the traceability system for fire alarms. A traceability system can be built for food packages, drug packages, etc. Similar communication is found in location-aware route guidance systems. There is a mode of communication that occurs among objects automatically also. The video clip I am going to show you cover a few topics. There are applications that can be realized by assigning identification numbers to objects, namely application for object, and there are applications for places in which we assign identification number to locations. There are combinations. But let us see a video clip that explains these applications to learn the concept more.
Use UCODE tags assigned to food packages. We record who produced the package, when and how it is transported, and over which route, as well as additional information, such as the type and amount of agrochemicals used during the growth of vegetable and fruits. Such traceability information is useful when a food incident occurs. By performing the process of backtracing, we can home in on the cause of the incident. In Japan, prototypes for such food traceability systems have been tested with the cooperation of many farmers, agricultural cooperatives, distributors, wholesalers, markets, and retailers. Using active sensors, we can continuously monitor the temperature of the food package during transport. In a futuristic scenario, we may one day have refrigerators that warn us of stale foods inside by reading the information on each product. UCODE tags can be used for positioning. Unlike GPS, UCODE tags can indicate current position with an error of only a few centimeters, even underground or inside buildings. UCODE tags offer pinpoint accuracy that GPS can't deliver, which is essential for pedestrian guidance. To illustrate just one application, let's look at how UCODEs can offer route guidance to the visually challenged.
Fork. Go left. You are near the south side of the Faculty of Engineering building.
Systems like these can help virtually anybody. They can assist the physically challenged, provide information for shoppers and sightseers, and give multilingual support to overseas tourists. The information can even be tailored to the user's precise time and location. For example, railway operation information can be automatically delivered from the railway company's server when commuters approach railway stations. Since 2002, numerous prototype services based on universal design have been installed in locations throughout Japan, including Tokyo, Kobe, and Nara. These systems are already in practical use every day in Japan. In Japan, a fire alarm must be installed in every home by law. This system, operated by the Center for Better Living, uses UCODEs for fire alarm maintenance. Tags are attached to the fire alarm units when they are shipped from factories. During installation, the system records who installed the fire alarm, as well as the time, date, and place of installation. The system notifies the center when batteries need replacing and sends out a request for recall if a manufacturing problem is found. Already about 2 million fire alarm units in Japan have been shipped with U-code tags. The National Geospatial Information Authority of Japan plans to attach U-codes to survey reference points. By using U-code tags to provide additional information about reference points it had previously measured, the government agency expects to lower the cost of third-party survey efforts. Other applications are just beginning, such as placing U-code tags on lampposts and other public facilities to provide sightseeing guidance. Applications in public facility management are already in use. Ubiquitous computing has taken root in Japan through numerous applications. As you can see, both the feasibility studies and commercialization have come a long way. Forecasts indicate that by 2015, commercial and public applications will be virtually everywhere.
I hope you now understand the open architecture, namely UID architecture, that uses U-code identification number has turned out to be useful to build the future IoT applications. Now I have come to the end of my talk. I have used the phrase open architecture to refer to UID architecture. That means the technical specifications will be made available freely to the public. Why? Because the technology for society-wide technological infrastructure should be under the control of the masses. It should not be under the control of single or few partners. Thus, the open architecture. Open source is just a component of open architecture. Source code alone is not enough. I would like to stress that freely available technical specifications, public APIs, manuals, etc. are also very important in addition to open source. For those of you who are interested in UID architecture, please visit the website of UID Center. You can even obtain 100 U-codes for your personal usage. If you are interested in TKNL, please visit the webpage of TNG Forum. If you are a serious developer, you can download the source code of TKNL from the web for free. By the way, there has been a port to Raspberry Pi CPU board done by a contributor lately too. We hold a large technological exhibition and symposium called TRON show each year. The next one is from 12th to 14th of December this year in Tokyo. If you plan a business trip to Japan in the next few months, why not schedule it so that you can visit TRON show in Tokyo? That's it. Thank you very much, and merci.